Hello, we are in section 3.3 and we're going to tackle our last objective, the normal and binormal vectors. Now, after taking a look at these normal and binormal vectors, we will continue on and discuss different aspects of these vectors that we're creating, and then figure out some other geometric aspects of the curves. Let's get started. So our normal and binormal vectors kind of are two of the second and third of our three vector frame that we're going to want to create. The first one actually is something that we've seen before, and that's the unit tangent vector, and it's pretty easy to define. We just find the tangent vector, r prime of t, and make it into a unit vector by dividing by its magnitude. So our unit tangent vector is going to be given by r prime of t divided by the magnitude of r prime, and of course that only works out as long as your r prime of t magnitude does not equal to 0. Now, to get our principal unit normal vector, we're going to take the derivative of our unit tangent vector. So the derivative of our unit tangent vector will eventually give us a normal vector that's going to be perpendicular to that. But it might not be a unit vector, so we divide by its magnitude again. So dividing by its magnitude will guarantee that this is going to be a unit vector. Now, it's principal because there are many different unit vectors to possibly have. Well, in 2D, let's take a look at the two-dimensional case. In 2D, your curve could be just doing something along a two-dimensional plane, and if we have our unit tangent vector, capital T, our unit normal vector, well, there's actually going to be two possibilities for our unit normal vector, and to make our principal unit vector unique, what we want to do is choose the one that's related to, well, it's going to be related to the second derivative. So it turns out that when you take the derivative of the unit tangent vector, you're going to be taking the derivative of this r prime of t divided by the magnitude of r prime of t, which will eventually get you some aspects of the second derivative. So if our acceleration, let's say our acceleration is pulling in some sort of direction, maybe our acceleration kind of looks like this. This is r double prime of t. Then out of these two unit vectors, we would choose this one because it's going in the same direction as the acceleration, generally the same direction. So that's in 2 dimensions. Now in 3D, it gets a little bit more difficult. You have 3-dimensional space, and you have a curve flying through that 3-dimensional space. And then your unit tangent vector, let's say, will look like this, but now your normal vector, there is an infinite number of normal vectors to choose from, right? So that's going to be really complicated, and to find the principal unit vector for this, what we're going to do is look for the acceleration again. So let's say the acceleration is over here. Well, let's maybe, I have no idea where the acceleration is going, but let's say the r double prime of t is pointing down or pointing in this direction. What we're going to do is we're going to construct a plane that contains your unit tangent vector, which is going in the same direction as your regular tangent vector, and your acceleration vector, and then whatever normal vector is on that plane will be the principal unit normal vector. Alright, so we'll eventually just call it the normal vector, but I wanted to kind of highlight the idea of the principal, meaning we have to choose the right one out of two possibilities or out of an infinite number of possibilities. And it's based on the acceleration. Okay, the last one is the binormal vector. It's going to be the vector that's perpendicular to both the tangent and the normal vectors. And here we don't need to divide by the magnitude anymore, because if you have two vectors that are perpendicular and that have unit length, then the binormal vector will necessarily be of unit length already. And you know that the magnitude of the cross product gives you the area of the parallelogram spanned by the two vectors. So these two vectors, the tangent vector and the normal vector, are already perpendicular, and so if we find the area of the parallelogram that it spans, you're really looking for the area of the square, and if we know that this is length 1, this is length 1, then the area is going to be 1, and so the magnitude of this is already going to be 1, so we don't need to divide by its magnitude anymore. Okay, so that's the binormal vector, and the binormal vector would be perpendicular to both the unit tangent and the unit normal vector in 3D. So the binormal vector does not exist here in 2 dimensions unless we want to look at the normal vector that's perpendicular to both of these, that would be going either out of the page or back behind the page, depending on the right hand rule where the t goes first. But in general, we don't bother with the binormal vector in 2 dimensions. So in 2D we just have the unit tangent and the unit normal, and in 3D we have all 3 of them. Let's take a look at some examples. Okay, here is a 2-dimensional example. We have a curve in 2D, and in this case they really just want one thing, right? They want the unit normal, but then for us to get that we need to find the unit tangent first. Okay, so let's do this. Let's find the unit tangent vector, and to do that we need to first find the derivative, and so the derivative of this is going to be 2t minus 3 in the first component, and then 4 in the second component, and the magnitude of that is going to be the square root of 2t minus 3 quantity squared plus 4 quantity squared. Generally you want to simplify this so that we can continue to work with it. And what do we have here? We have a 4t squared minus 2 times 3 is 6, double that, that's 12t, and then plus 9, and then plus 4 squared is 16. Alright, we end up with the square root of 4t squared minus 12t plus 9 plus 16, I think it's 25. And I don't believe we can simplify this much more. Okay, so let's just leave it like that, and we finally get our unit tangent vector to be this thing. I'm going to keep this outside instead of putting it all under one denominator, so I'm going to keep it outside as a 4t squared minus 12t plus 25 to the negative 1/2 power, because that goes in the denominator, and then multiplying it by 2t minus 3 comma 4. Okay, so that is our unit tangent vector. So now we want to find this at 2, at t is equal to 2. So let's put 2 in here. And then we will get, well, what are we going to get? Let's put 2 in here. T is equal to 2. Then r prime of 2 magnitude is going to be the square root of, what do we have? 16 minus 24 plus 25. So I think this is a positive 1, so that's root 17. So this is square root of 17. Let's put a t in here, 2 in here for t. We're going to get 4 minus 1, and then 4. So our unit tangent vector at 2 is going to be, well, I'm going to write it differently again. I can write it like this, or we can write 1 over square root of 17 comma 4 over square root of 17. Let's do both. Okay, so now we have our unit tangent vector. Now this is in 2 dimensions. If we need to find the unit normal vector, according to the formula, this is the derivative of the unit tangent vector, and after you take the derivative, this may not be a unit vector, so we're going to divide by the magnitude of its derivative. Now you can kind of see that we would have to take the derivative of this expression t here, which does not look nice. There's definitely a formula for this where we have a scalar times a vector, so the scalar multiplication, the derivative of that will require some scalar multiplication product rule that we've seen in derivatives, which may seem kind of easy in theory, but when you actually try to do it, it gets a lot more difficult. So instead of using the formula, we're going to do something else. We know that this curve is in 2 dimensions, so this curve is in 2 dimensions. It's probably parabolic looking, right? So it kind of looks like a parabola-ish, and since the x is being squared and the y is not, it's probably going to be some sideways parabola. I don't know exactly how it's going to look like, so let's just say it looks like something like this, and t is equal to 2, it would be somewhere, I don't know, over here. We have the graph that has a unit tangent vector. Let's say we found the unit tangent vector, so this is both positive, 1 and 4 are both positive, and so it's going to be pointing towards the first quadrant if you put it back at the origin. Now there are 2 possibilities for a normal vector, right? So these are our 2 candidates for a normal vector, and they have to be perpendicular. So if we have 1 over root 17 and 4 over root 17, they already make a unit vector out of this. So we can use these very same numbers and then find a way so that the dot product is equal to 0. So in other words, we want to find 2 numbers, a and b. So let's say this is equal to a and b. Those are scalars inside of a vector form, so that t dotted with n is going to equal to 0. So t is 1 over root 17, comma 4 over root 17, dotted with a and b, and we want that to be equal to 0. Well, what we can do is we can switch the order. We can have 4 over root 17 and 1 over root 17, and then make one of these equal to negative, or not equal to, but make one into a negative. And if we take the dot product, then it would be equal to 0. So this is one candidate, and this is another candidate. 4 over root 17, negative 1 over root 17. So these are our two possibilities for the normal vector. This one has a negative x, so negative x, positive y is this one, so let's call this one possibility 1 and 1, and this one would be n2. And so we have to decide which one it is. And so the way to decide would be to take our, remember that this is going to be on the side of the actual second derivative. So let's find the second derivative, r double prime of t. So this is r prime of t, so r double prime would be positive 2 comma derivative for 0, so 2 0. So what is that? It would be the second derivative goes like this. So it looks like it's pointing in the same side as n2. So and I'll put same direction, and I'll put same in quotes because it's kind of looking at the general direction of which is pointing. So it's not going to be n1 because it's pointing in the other way, so it's going to be n2. So this is going to be our normal vector. So your normal vector at 2 in particular is going to be a positive 4 over root 17 comma negative 1 over root 17. And then that's it. So that would be your result. Again, if we were to try to take the derivative of t here, it gets really complicated. So that would be really the way to go in terms of the formula. But since we're dealing with something in 2 dimensions, it's not too bad. All right, let's do another problem. This time let's do it in 3 dimensions, and this time we're looking at not just the t and the n, but also the binormal vector, the b. So let's take the derivative. We will have r prime of t is equal to, so derivative cosine is negative sine. There's a 2 here, and an extra 2 would come out when we do the chain rule. So we'll have negative 4 sine 2t. And same idea here for cosine 2t, and then a 2. And now we want its magnitude. R prime of t magnitude is equal to the square root of 4 squared sine squared 2t plus 4 squared cosine squared 2t plus 2 squared. So we got the cosine squared and the sine squared business happening there. Factor out of 4 squared, that's 16, and 16 plus 4 is 20. So we got root 20. And then we have our unit tangent vector. And I'm going to go ahead and distribute this scalar 1 over root 20 inside. So this is a negative 4 over root 20 sine 2t comma positive 4 over root 20 cosine 2t comma 2 over root 20. Okay. All right, now we want this at 0, so let's calculate this when little t is equal to 0. And this will give us sine of 0 is 0, and cosine of 0 is 1, so this is 4 over root 20, and then we have 2 over root 20. And I encourage you to take the magnitude of that and show that it actually is equal to 1. We can probably do some simplifying here, but let's just leave it like that. Alright, now to find our normal vector, remember the formula for the unit normal vector is t prime over the magnitude of t prime. So we need to find t prime, capital T prime that is. So capital T prime, the derivative of the unit tangent vector, is going to be, alright, 2 comes out, derivative sign is cosine, but there's a negative already out. The 2 out would be, make this into an 8 over root 20. That's a cosine 2t. There's a missing parentheses there. Derivative of cosine is negative sine, 8 over root 20, sine 2t. And then the derivative of this last one is going to be 0. So that's good. That's gone. And this magnitude might not be equal to 1, so let's actually find the magnitude so that it does equal to 1. So that will eventually make it equal to 1. So the magnitude of this is equal to, let's see, the square root of 64 over 20 cosine squared 2t, and that'll be positive because it was squared, and another 64 over 20 sine squared 2t, and then 0 because the last part is 0. So we factor out a 64 over 20 under a square root, and then that just leaves us with 1 with a sine squared and a cosine squared. I believe this is 8 over root 20, and so we're going to divide out by 8 over root 20. So your n vector, your normal vector, your unit normal vector, your principal unit normal vector will have this thing divided by 8 over 20. So we see that they have coefficients of 8 over root 20 that would divide out, and so that would just cancel everything, and it'll leave us with a negative cosine 2t, negative sine 2t, comma 0. And if you were to take the magnitude of that, you'll see that the magnitude is equal to 1. But more specifically, we want our n evaluated at 0, and derivative, cosine of 0 is 1, sine of 0 is 0, so this is our unit normal vector. Okay. Now to get our binormal, it's going to be the t first and then the n. And let's just use these two already figured out values because we want it specifically at the t is equal to 0. So this is going to be the cross product between 0, 4 over root 20, 2 over root 20, cross negative 1, 0, 0. So the cross product will be, if you imagine this written vertically, let's write it here, negative 1, 0, 0. So the first component would be 0 and 0. The second component would be negative, and then that's gone negative, negative, so that's a positive 2 over root 20. So there's positive here that makes this a negative eventually, and then the last component would be a 0 minus negative 4 over root 20. So 0 minus negative, negative, 0 minus negative 4 over root 20 will give us a positive. So this would be 0 negative 2 over root 20 and positive 4 over root 20. So this should be perpendicular to n and t at the same time, and that would be your unit vector. Okay.